of work. We'll talk about estimating Hausdorff dimension for hyperbolic Julia sets.
Thank you very much. Let me begin by saying that it's a great pleasure to be in Bedlevo again and to thank the organizers for their kind invitation. So since the conference is apparently about Julia sets and their complexity, I decided I would try to make an effort to talk about Julia sets and something to do with complexity. Subjects about which I know very little, so that may not add to the depth of the talk, but I'm hoping that other things will compensate. By way of some sort of audience participation, could you raise your hand if you have attended a talk that I've given before? I have. Could you keep your hand up if you've attended a talk in which I've given out chocolate? Okay, then you're in for a treat again because I'm going to hand out chocolate yet again. Why I do this is now beyond me, but I do it at every talk, and so now these are all for Carl Roy, but he may share them with you if you're lucky. Okay, so what I wanted to do was to say something about Julia sets. So I've attempted to write something about Julia sets on the board. This is about everything I know about Julia sets, so the rest of the talk will not contain too much about the details. So basically, I'm interested in the Julia set, which I'm thinking of as being some nice compact set sitting inside the complex plane, in the cases I'm interested in. It's given by a rational map, for example. And then the Julia set you can just define to be the closure of the repelling periodic points. So it's a nice set, perhaps a rather complicated structure. And for the purposes of this talk, I'm going to assume that these Julia sets are all hyperbolic, which just means that when you restrict the map to the set, then the derivative is strictly bigger than 1. And that's the setting in which I want to consider things. In fact, nothing I'm going to do in this talk is restricted to this setting. It would work more generally in the following context. I could just have some compact set sitting inside a finite dimensional Euclidean space. And then my transformation, I would just require to be C2, twice differentiable continuous second derivative, and the map to be conformal. Conformal is something you like to assume in this context if you're going to talk about dimension. And in this case, the map T would be a repeller, which just means that locally points move apart by some bounded amount bigger than 1. So it's a locally distance expanding map. So this is a context in which what I'm going to say would work, but we can focus on the specific setting for this conference of Julia sets. Okay, so having set up the sort of setting I'm interested in, I want to talk about the complexity. And in order to do that, I want to talk about the dimension of these sets. So everyone is very familiar with the dimension. And so having already written down something else, so the complexity I want to quantify. The quantity will be a numerical value, and it will be the dimension of this set J. And so typically one talks about the Hausdorff dimension of the Julia set, or the set you're interested in. Fortunately, in this context, the Hausdorff dimension turns out to be the same as the box dimension or the Minkowski dimension, which has the considerable advantage that the definition is much easier. So thus, I just recall the definition of the dimension, in this case, Hausdorff or box dimension of the Julia set. So if you imagine that the Julia set is this blue squiggly curve, it doesn't look very fractal, but I can't draw very fractal sets freehand, then the definition is the usual one. You choose some small value epsilon greater than 0. You cover this by epsilon balls of radius epsilon, and then you choose the smallest number of balls needed to cover it, and it will be some number which depends on epsilon, n of epsilon. And then the dimension is the growth rate of this quantity as epsilon tends to 0. Or more specifically, it'll be the limit as epsilon tends to 0 of the logarithm of the number of balls needed to, epsilon balls needed to cover the set, divided by the log of 1 over epsilon, letting epsilon tend to 0. And in this particular context, this limit will exist. Generally, it might not. And moreover, it'll be some value which is between 0 and 2 if we're talking about Julia sets. So the dimension of a Julia set will be a numerical value which is somewhere between 0 and 2, and this is at least one definition that we can use to define this set. So we have our set. It's defined using a transformation T, and then we have a notion of how large it is or how complicated it is, which is the usual idea of dimension of a set. Correct. So in higher dimensions, we count higher dimensional balls or boxes, and there are various other simplified, maybe Artem wants chocolates or not, I don't know. So there may, in high dimensions, the definition just generalizes in a nice way, which we can all read about in books by Faulkner or maybe Przitsky and Urbanski, all these other classic texts of literature. Okay, so we have our set. It came from a transformation. We have a numerical value, its dimension. And you can ask yourself, well, what is this number? If we're given a specific transformation, a specific rational map, it gives us a very specific set. We know its dimension is some numerical value. How can we actually estimate it? There's no particular reason it should be equal to a well-known value, pi squared over 12 or something, but it may just be some real number we might want to estimate. And then another question is, why would you want to do this anyway? But that's not a question I'm planning to address. So I will stick to the question of how can we estimate this in this particular setting. So the main point is that we don't particularly want to work with this definition because this convergence may be quite slow. So I could take a sequence of epsilons and try to compute what this is, but I have no idea how fast it's going to converge to this value. And it may give very bad estimates. So we need an indirect approach, or at least another approach, to trying to estimate this value of a dimension associated to the Julia set coming from my transformation T. And so I will introduce some smooth ergodic theory. And in this case, it's going to be, Artem looks a bit like a waiter carrying around a tray. It's very impressive. An indirect approach is to use something called the pressure function. So the pressure function is a pretentious name for just a function associated to my transformation and my Julia set. And so it's a function that maps us from the real numbers to the real numbers. And the way so here's a plot of it. So here's the real axis. This is t. This is my plot of p of t. And so it's meant to be a function associated to the transformation t, the rational map. And how is it associated? Well, it measures another kind of growth rate. And the way it's defined is the following. You take a value t appears here. So t is just a real number. And then for each n, we look for the number of fixed points for n iterates of a transformation. So essentially periodic points of period n, of which there are maybe 2 to the n or something. And we're interested specifically in this multiplier. So we see how the derivative around the orbit of period n grows. So we're taking the absolute value here. So it's how it expands around the periodic orbit of period n. And we sum these guys up over all points of the same period. So you give me n, we look at all periodic points of period n, or fixed points for t to the n. And then for each of these, we look at the derivative around the orbit, and we raise it to the power minus t. So the derivative is going to be bigger than 1, so this will be some number which is smaller than 1 if t is positive. And then we define the pressure to be the limit as n tends to infinity of this quantity. So it may not look immediately like it's an advantage over the original definition, but it does have some merits, as I hope will become apparent soon. And the properties of this function, from the real numbers to the real numbers, associated to my transformation, the rational map restricted to the Julia set, is the following I've listed. So first of all, as indicated in this rather elegant graph, you could believe that this curve is going to be smooth. It's actually real analytic, but smooth is good enough. It's strictly decreasing, which possibly one could guess from the definition. And the more interesting property is that there is a value where it crosses the axis at this value here, and this point here turns out to be the value of the dimension of the set, the value we're interested in. So over here, the dimension was given explicitly as a limit, as epsilon tended to 0. Here, the dimension appears implicitly in terms of this function p of t. And so these properties were studied way back, probably in the 1970s, possibly 60s. The characterization of the Hausdorff dimension in terms of this function, so P stands for pressure, the characterization in terms of pressure was implicit in work of Bowen from 1978. This was not about rational maps. This was about quasi-circles and quasi-Fuchsian groups, kind of related stuff. Unfortunately, Bowen was unable to elaborate on this work because he died the same year. And it was taken up 4 years later in an article by Ruel, where he talked rather specifically about Julia sets following some lectures he attended by Dennis Sullivan. It's interesting, you can hear me breathing, so that's a good sign I'm still alive. Okay, so these great guys were responsible for this characterization of the Hausdorff dimension, or just dimension of the Julia set, given by that definition over here, but this characterization is in terms of this function. And the big question you might ask is, well, it looks more complicated than the original definition, so how are we any better off? Well, we are better off because there are now ways to estimate the pressure function, and the pressure function therefore gives us insight into the dimension. So having got almost 15 minutes into the talk, I actually have to write something. So let me do that. So there are actually 3 different methods I want to talk about on how to estimate this function. So 3 different methods. Two of them are actually from this millennium, so that's kind of more relevant. And so they're basically what I might call the finite section method. Which basically involves looking at matrices. And the second one I will blithely call a zeta function method. It's not really zeta functions, but it's a good thing to write in talks. And thirdly, something called the minimax method, which is not really a minimax method either, but it's also a good title. It's much better to have memorable titles for things than actually accurate titles, perhaps. So I want to talk about these 3 different approaches. So let me start with the first one. And so this is what I've called the finite section method. And so this was an approach popularized by Kurt McMullen in an article from 1998. So McMullen wrote 3 papers in a series, numbered 1, 2, 3. And if you look at the publication dates, number 3 appeared first, and then the second one appeared second, and the first one appeared third. I'm not entirely sure what that tells us about journals, editors, or referees, but it's kind of intriguing. And this approach actually has earlier versions, for example, in the book of Pallas and Tarkins, not for Julia sets, but for other settings. This is from 1993, published by Cambridge University Press. And even further back, you can relate it to the so-called Ulam method, which is not for dimension at all, but it has a similar sort of flavor. And how does this go? Well, the idea here is that you want to replace your Julia set by some sort of partition. So let's assume that we partition it up into pieces. This is meant to be a partition. What kind of partition would it be? Well, I'm thinking specifically of a Markov partition, which I'm sure we are all familiar with, but we don't need to be because I'm going to illustrate it with an example. And the point here is that if we want to estimate this complicated expression, the difficulty is that we might guess how many periodic points there are of a particular period. It's kind of harder to guess the actual multiplier around that value. So therefore, we want to approximate it by something else. And so, in fact, we can approximate the somewhat troublesome derivative by some locally constant function. So we might say that on a particular part of this Julia set, I'm assuming that these have disjoint interiors, we get that the derivative restricted to this piece is going to be bounded above and below by two values. And rather than elaborate this in any particular way, let me just say it's illustrated. Maybe best illustrated by an example. So let me give a very simple sort of example. It's not a very specific example, but let me do it that way. Let me get rid of the definition since we don't need it. And you can ask any question you like.
If the Hausdorff and the box dimension are equal in this context, is it a theorem?
Yes, it's a statement which is in fact true in this case, and it follows simply from it follows from the results which are in these two articles. Yeah. There's a very nice treatment of these things in the books of Falconer, which explain it relatively well. I mean, it's a feature of the fact we're working in the specific case of hyperbolic attractors. Otherwise, we might be in more of a complicated setting. So let me put an example. And so it's not the most exciting of examples. So let's imagine that we have a quadratic map. But I'm also going to assume that the absolute value of C is small. And what do I mean by small? I mean, in particular, I want that the set J is just going to be a quasi-circle. So if C was equal to 0, it would be precisely a circle, but more generally, it will be some wobbly-looking circle, which looks something like that. That's meant to be my Julia set. So the absolute value of C is small enough so that I get a quasi-circle here. And then I can look for a point here. This is going to be a fixed point. And from this fixed point, I'm going to do the following. I'll let K be large. Well, let me say K is a natural number, and it's going to be large. What does large mean? Let's say 20. 20 is kind of large. And then I'll take n to be, say, 2 to the k. And then in particular, the idea is that I want to look at pre-images under the map t to the k of the point x0. So I look at t to the minus k applied to x0. And this will give me some collection of points, which I'll call x subscript I. So this is a fixed point, so x0 should be one of them. And we're going to go up to, hopefully, n minus 1, maybe. There's always room for error in these mistakes. And then what I'll do is I'll draw on this picture, particularly if I can find the yellow chalk. So there's going to be a bunch of points around here, which are the pre-images. And let's imagine that I index them in some suitable way. So let's call this x1, x2, x3, xi plus 1, around to maybe this guy's going to be x, whatever's left, n minus 1. And these are all pre-images under k iterates of the map like that. Very illustrative picture. Okay, so these are my pre-images, and so in particular, I can choose my partition, which I was a bit cryptic about before, up to n-1, just to be these various bits between the points. So here might be this piece here. This will be ji, I guess. So I'm partitioning the set up into these pieces, which I'm calling ji. They overlap at the endpoints, which are the points xi, but I don't care. It just gives me a way of chopping up the space into these various guys. And then, so I could write this maybe as xi plus 1, just to represent that it corresponds to the arc. So let's assume I have this sort of picture. So now I partition my setup. If I had the blue chalk, this one will become J1. No, this one will become J0. This will be J1, etc. And then if my notation holds together in some sort of reasonable way, what happens if we apply the transformation to the piece Ji, where I is between 0 and n-1? Well, there's a possibility that it's going to be equal to J2I, maybe mod n, union 2I plus 1 mod n. Might not be equal to that, depending on whether I get the calculation correctly. But the basic idea is that you're taking one of these pieces and you're applying the transformation, and it blows up to give you two more. So let's imagine that it goes down to, say, these two pieces down here under T. Okay, how does any of this help us? Well, what we'd like to do is to find some way to make sense of estimating this quantity using these bounds. And so in particular, we're going to do the following. So for T, a real number, because T appears in this formula, I want to define two matrices. So define two n by n matrices, which I will call something. How about m underscore t, which I have entries I and j, and the other matrix will be t overscore ij. So they depend on t, and the way they're defined are, I'll define mt bar ij. What's it going to do? It's going to simply be equal to the supremum of the derivative of the map at a point z, providing we are inside the piece ji. And we only do this if we have that the value j is where you go to from the interval t of I. So that would be if j is equal to ti or ti plus 1, give or take mod n. And otherwise, it's going to be equal to 0. So I can define one of my matrices in this way. It'd probably be slightly more intelligent if I'd done it the other way around, which is to call this the supremum, the overscore meaning supremum. And then we similarly define the other matrix, which will involve replacing this by...
excuse me? We need to raise to power t minus t.
We do need to raise it to the power c, otherwise there is no point in putting it. See here, thank you very much. And similarly, should I write down the other matrix? Maybe I will. And the other matrix looks exactly the same, except I'm going to replace the supremum by an infimum. At least if I don't do that, then you'll know I've got it wrong. So m lowest score t ij is going to be equal to, as I claimed, it should be the infimum if z is in ji of the derivative of the map at the value z raised to the power minus t, or it's going to be 0. And it's this first case again if J is equal to either 2i or 2i plus 1 mod n, or it's going to be 0 otherwise. Whoops, otherwise. So all it's doing basically is keeping track of the expansion on the Julia set J, but bounding what happens on each of the pieces by these two values of the infimum or the supremum. Now I'm worried that since I put the minus sign in, I should have put the matrices the other way around. So let me risk doing that. Well, let's see where it gets us. Okay, and then it claims here an easy exercise, which means I'm not going to do it. Exercise is that, well, these are just matrices. They're n by n matrices, and we can associate to them an eigenvalue. They have a maximal eigenvalue. So let's say that m bar of t has a maximal positive eigenvalue, which is going to be equal to, I'll denote it by e to the p of t. I'll put a bar on the top. And let's assume that the other matrix, which is with the underscore, has a maximal eigenvalue, which will be e to the p underscore of t. This is just notation. So I've got the expanding map. It's defined on this Julia set. And then on each of these pieces, one can do something. One can approximate what the derivative looks like by just the largest value and the smallest value, just raised to the power t, because that's what we did in the expression up here. And then if we define these, then what should happen, if I got it the right way round, is that the function p of t, which is just coming from this eigenvalue, coming from a finite matrix, is bigger than p of t, is bigger than p lower of t. It's either this way or the other way around. And the point is that these two guys are easy to compute. And now, if we remember this picture, which is up here, and in fact, if we draw on it, we can now plot on this picture these functions which come from the maximal eigenvalues, and this will give us two more functions, which look a bit like that. For any value of t, one is bigger than the other. So let's assume that p of t is bigger than this, and this guy is going to be t lower of t. Well, they will cross the axis at 2 points, which we can call d lower bar and d upper bar. So here we get that p bar, d bar is defined to be the value, whoops, wrong way around. It's going to be the value for which this is 0, and we choose d lower score to be the value for which the pressure function, this new pressure function coming from the matrix, crosses 0. And then in particular, we get that the dimension of the set is bigger than d lower bar and it's less than d upper bar. So if you wanted to get upper and lower bounds on the dimension, one way to do it is to simply replace the problem by a finite problem, a matrix whose entries are simply approximating above and below the derivative at these values, and then you get this inequality here. So it's very easy to do. It has the advantage that
excuse me?
Yeah.
A question. When you say it's very easy to do, you need to take maximum subsummum infimum over a piece of Julia set. So you need to have some approximation.
Yeah.
Julia set, right?
Yeah.
So how do you do the approximation?
Well, there's a markup published for the Julia set, and the derivative is PC1 on there. We know how big the pieces are of the Julia set, so we could bound it from that. Just choose any point inside there, and then to see one function, you can just use the various principles to be valued there, for example, to get a bound on the derivative. And of course, I fixed the value of k somewhere near the beginning. Somewhere on these boards. Here, I chose k and said it should be large. And so the larger k is, then the closer these two bounds get. So these are closer for larger k. Unfortunately, as k gets bigger, it means that your matrices are getting bigger, and so it gets harder to actually compute the maximal eigenvalues. So there's a payoff between these two things. So this method has been around for a long time, and there are two other methods I'd like to squeeze in. And so let me talk about that. What's going to go first? Maybe this one will go. So the second method I mentioned was to use zeta functions. So zeta functions are not exactly zeta functions, but they have a lot in common with zeta functions, i.e. they're functions of a complex variable. And in particular, they are dynamical objects. They're again defined in terms of the periodic points for the transformation, but you should think of them as being a kind of way to reorganize the information. So this is going to be the second approach, and this is an approach which was used by Oliver Jenkinson and myself, that dates back to 2002, so it's just inside the millennium. And so the idea is it reorganizes, so it organizes the data on the derivatives. X is an element of fix t to the n in a different way. In a different way. So briefly, the idea is that we define a zeta function, which is a complex function. So formally, it's defined as follows, where z is just a complex variable. And the way it's defined is we say that zeta z of t. T is the value that's going to, is again the parameter value defined, which defines the pressure function. And so this is formally defined to be some exponential of a certain power series. And the power series is in z. So it's like, that's like a generating function of some kind. And then there's an expression here, Zn of t, which I won't explicitly give, not because it's very complicated, but it is a bit elaborate. And this expression here is some expression in terms of what? In terms of this data again. So it's in terms of the values t to the n prime of x, absolute value, where x is an element of fix t to the n. So for each n, the nth coefficient in this series is just based on these values. And when I talk about reorganization, oh, well, let me just say what the point of this is. So this is a complex function, and it has an extension in the entire complex plane. It's a meromorphic function. In fact, it's an entire function. If I get the signs right, there should be a minus sign there. And then in particular, what happens is, as a function, it has a 0 at the value p to the minus t. So in this case, the statement is that if you take z to be equal to e to the minus p of t in the analytic extension of this function, then this value here is 0. i.e. zeta of this value, e to the minus p of t at t takes the value 0. That's what it means to be a 0. So,
sorry, question?
Yeah.
Do have restrictions on values of t for this to be true?
No, for any value of t, this series will converge, providing the absolute value of z is small enough. And then there's a theorem that says that it extends as an entire function to the complex plane. So it's defined for all t. Yeah, so this is fine, but does that help us at all? Well, I said that it reorganized the the information about the weights of the periodic orbits, and the idea is that somehow this should help us to get better estimates on the pressure function. So how does this reorganization work? Or as it says in my notes, problem. How does this help? Help estimate the value P of t for any value of t. And the answer is the following. You expand it in Z as a power series. So we can just think of this as a function of Z, and then we can write that Z for a fixed value of t, this function is going to be 1 plus some series, n equals 1 to infinity, an, coefficients depending on t, times z to the n. So it's just a complex function. And if we wanted to estimate this, understand this function to evaluate where the zeros are, then it's a bit complicated having an infinite series. So we can write this as a finite series. So we could truncate it and write n equals 1 up to some big value. Let me call it m. So that would be an of t, z to the n, plus whatever's left. And whatever's left is of the form alpha to the m squared. So what are these values? This is where alpha is some value between 0 and 1. It's basically just related to this expansion that we have. It's the reciprocal of the lower bound on the derivative of the map on the Julia set, more or less. And these terms here are explicit in terms of the weights t to the n prime of x. It's a bit jumbled up. So the nth term would actually be explicit in terms of the values where L is less than or equal to n. So now we have a polynomial of degree, presumably m, plus some error term. But the important thing here is that this value here, this expression here is very small, because this is smaller than 1, and we're raising it not to the power m, but to m squared. So if m was something like 20, then we'd be looking at alpha to the power 400, which is kind of tiny. And so in particular, you get that this is a very good approximation to this. And so the zeros of this are very good approximations to this. So this is a polynomial approximation. And the zero of the polynomial is going to be approximately e to the minus pressure of t. That's the thing we're looking for, plus an error, which will be of the same order as this. So it's alpha to the m squared. So it's a very tiny error with not too much work. So this is just another approach, which is quite efficient if you're looking for moderate accuracy. It gets more complicated if you want very accurate terms, because estimates on the dimension, like to 100 decimal places, because you have to work out all of these weights for periods up to 20, 30, something like that. And 2 to the 20 is kind of a large number. And so consequently, it has certain disadvantages in that respect. So in the remaining 8 minutes, let me talk about a third method of doing this. And so thus far, the first method just took, all three methods make use of the characterization in terms of the pressure. Maybe I'll leave that one up. The first method simply did an approximation to the definition of the pressure, where the derivative was bounded above and below on various bits of the set. The second one kind of reorganized the material, the weights, using a complex function. And the third method uses a bit more operator theory, but is actually much more straightforward. So let me go back to the third method, which is called the min-max method. And this is yet another another characterization. American spelling of this value P of T, the pressure function, which gives us a dimension from its 0. And so the idea here is that I had before, when I was talking about this method, the first method, I was partitioning the Julia set up into various pieces. So my Julia set, this is maybe J1, J2, etc. And so what I want to do now is I will consider such a partition, and I will choose an open neighborhood, or just a neighborhood maybe, of each piece. So the idea is that for each of these pieces, I'm going to choose, let's say the ith place is going to be Ji. I'm going to choose an open neighborhood of this, which I will call Ui, for no particular reason. And then what I want to do is, I will choose these such that if I have that the image of Ji contains Jj, it's a Markov partition. So if the image of this guy, if he gets mapped somewhere, let's say he gets mapped over here somewhere, like this, but this guy is going to be Jj, maybe it'll be white chalk, this will be Jj, this guy. Then I want that the image of this yellow set, which will be T of Ui, should contain the open set associated to the first guy. So this will be this guy. This will be U subscript J. So that's what this is meant to mean. So if this is true, then T of U of I contains U of J. I also want it to be a diffeomorphism on these sets, but let me not labor these points. Why have I introduced these open sets? Well, I've done it because I want to define a space of functions. So I'll look at the C1 functions on this set. So this is 0 up to, I've forgotten how many there are now. So let's say that I is between 0 and n minus 1. So up to n minus 1. So I look at the union of these sets, and I want to look at C1 functions on here. And this is basically a Banach space. It works slightly better if I look at the closure of the intervals. Maybe I'll just put that in there. And this is just going to be a space of C1 functions. This symbol just means a disjoint union. So if I have an overlap of neighboring open sets, I think of them as being disjoint. I don't worry about the union being in the space. Why have I introduced this space? Well, because I want to introduce a transfer operator. And a transfer operator is just a linear operator on this space. So that's C1 union I equals 0, n minus 1, Ui to itself. And what it does is it just uses the transformation T and the weight little t in R to make sense of things. So the definition is going to be LT of some function. So my function is in my space. So this is C1 I equals 0 to n minus 1 Ui bar. And how is it defined? Well, at a point x. So x is going to be in this space. I want to get another function in the same space. And what I do is I sum over the pre-images of my point x. So if my point x is up here, I sum up over pre-images of that. And then I weight it by t prime of y to the power t, maybe minus t is even better, of w of y. So in my set, which I think will be again white, here's my Julia set. So for any point x, I look at the points that map onto it. So maybe y. I'm averaging the function w into the reals, I guess, over these pre-images. So I'm summing up over the pre-images, but I'm weighting them according to this derivative. And this is what's called a transfer operator. It made a guest appearance yesterday in Anna's talk, as indeed did the pressure function. So now I have a family of operators, depending on this parameter t, which are supposed to help me estimate the pressure. Well, the way it does that is because now I have my rational map. I have my hyperbolic Julia set. So I've got T mapping J to J. I'm looking at functions on neighborhoods of this Julia set, and I'm defining an operator on these functions. Now, one could characterize the pressure as an eigenvalue, a maximal eigenvalue for this operator, acting on this Banach space. But in fact, I'll skip a step and I'll conclude from that the result. And so the theorem that encapsulates this estimate is the following. We can say that given two values, T0 and T1, the dimension of the Julia set will lie between those two values if something is true. And it will be true if we can find functions W0 and W1. So these are defined as functions in a neighborhood of my Julia, pieces of the Julia set, defined in this way. And they should have some property, otherwise there's no content. And the property should be that if I apply the transfer operator, this operator with the weight t being T0, then what it should do is make the function W bigger. So this should be bigger than W0 x. This is for all x in the set. And also, so let me write it down, all x in the disjoint union I equals 0 to n minus 1 of u of I. And similarly, LT0 of W of x, except that should be W0. This should be W1. So if the second function gets smaller when I apply the operator with the weight T1, so all the zeros become ones here. And if it gets a smaller function, and this should be true for all x in this union I equals 0, n minus 1 of ui. So if that's true, we can find such functions, then it gives us bounds above and below on the dimension of this set. So the pictorial image is that if my space, that's the union I, ui, was an interval, which it isn't, but it looks better in the picture, and I were to take my function W0, then I want that when I apply the transfer operator, it should get bigger. So L, T0, W0. So every point X, it should have gone up. And the picture over here is that if I have my function W1, and I can find such a function so that when I apply the operator, it goes down. So this would be LT1, W1, then in fact, it will imply these bounds on the dimension. So basically,
excuse me.
Yes.
Do you need W0, W1 be positive?
Yes, we need them to be positive. So this I skipped in my definition. They should be R greater than 0. Thank you. And then in particular, so final question is, where do they come from? Well, in fact, you could guess them, but that would be hard work. Another possibility is to use ideas from numerical analysis, so you can use interpolation theory. From numerical analysis. And so in particular, you could think of this theorem as being a way to make guesses, which comes from these approximations, into rigorous bounds. And it leads to quite accurate estimates with very little work in lots of cases. And so if you give me 1 minute, I would draw one example, and that will be it. Or I might draw 2 examples if I feel particularly indulgent. So In the first example, when I was talking about the McMullen method, I talked about a quasi-circle because that's a very easy way to see the Markov partition in that case. But it's not necessarily a great example, but you can try to apply this method in that case. So these open neighborhoods, for example, you could take as follows. So here's an example. So example 1. So I go back to the case of quasi-circles. So here's my quasi-circle again. And there was a Markov partition associated to this. Well, the simplest one would be to take x0 and its pre-image. This is the fixed point for the map. The pre-image would be, say, this value x1. So therefore, there are two pieces to the Markov partition, J0 and J1. The parts between x0 and x1, and then x1 and x0. And so in this case, you could simply take the neighborhood. If I could find some nice chalk, I think it's going to have to be blue. So we could take the neighborhood, or it could be yellow even better. In this case, we could take some sort of annulus incorporating this, providing C is small enough, like that. And then we need that this property about when you blow up the annulus, it covers itself. So here we could take U0 to be U1 to be this annulus. And another example would be the following. So this will be my unique opportunity to draw a basilica set. So here it's meant to be a basilica. It looks, so this corresponds to C is equal to -1. So it looks a bit like this. So in this case, there's a Markov partition which contains 4 elements. And the 4 elements correspond, for example, to, if I draw a dotted line across here and a line through here and through here, then the 4 pieces might be J1, J2, J3, and J4. And somewhere in here, there is -1, 0, and possibly 1. So in that case, you want to look at 4 open neighborhoods. And so in this case, we could choose the neighborhoods U1, U2, U3, and U4 be the same as U3 to be annuli. So in this picture, we have 4 annuli of some specific radius looking something like that, centered at these 4 values, 3 values, 0, 1, and -1. So that would be U1, U3 is equal to U4, and this would be equal to U2. Okay, thank you very much.
Questions, comments? Okay.
Well, have you tried to check which of the 3 methods is computationally the fastest?
Depends on the examples you're interested in. So they all have pros and cons. So if you have a reasonably hyperbolic, whatever that means, it means the derivative is quite big, then the second method is quite efficient using zeta functions. If the less hyperbolicity you get, or the more complicated the set is, then I suspect the third method is the more efficient. But if you just want a rough and ready answer, then the first one serves sufficiently well. If you only want 1 or 2 decimal places, I go for the first one. And then if you want more decimal places, or I go for the second one, or if you want something that's got more decimal places and is easier to check the error estimates, the third one is best.
Nomial time complexity?
It could be worse than that, really.
Yes.
Which of the 3 methods is more robust to the hypothesis of hyperbolicity? Okay, so
I would suspect the third one is probably the best in terms of that. The second one is very dependent on it being reasonably hyperbolic. And the first method, it's harder to estimate the error terms. I mean, you can get bounds, but they're a bit a priori. So one has, or maybe a posteriori. But my favorite's the third one, basically, at this moment.
I have a question. Could you give an idea why in the second method you get error of the form alpha power m square, not m?
Yeah. So I mentioned that this paper of Ruel from 1982, where he talks about estimating the Hausdorff dimension in terms of the pressure. So in there, he refers to zeta functions. And there was a previous paper of Ruel from 1976, when he was not interested in dimension, but he was interested in dynamical zeta functions for hyperbolic systems. And there, you assume analyticity. Analyticity is very important. Because he used ideas from the work of Grothendieck. So before Grothendieck was an Ital cohomology guy, he was a Banach space guy back in the 1950s. And he has some very nice memoirs written in French in which he talks about taking traces of operators. And it turns out that in that case, the underlying transfer operator is what's called a nuclear operator, in particular it's compact. And for these estimates come out of his work. So we're piggybacking on the work of Grothendieck, basically.
Any more questions, comments? If not, let us assume at 5 minutes past 10.